Well, welcome to the second to last talk on Wednesday afternoon, UGM 2021. I'm Terrell Russell. I'm currently serving as the Chief Technologist for the iRODS Consortium. And I'm going to talk about some work that I've done with some people here at UNC and kind of go through the process of how we did it. And I'm hoping that that becomes instructive to someone else as they kind of go through this process as well. So the title is iRODS Policy. It's a read-only policy for local analysis. And it's a staging policy for Braini. So this project is what you heard about a little bit earlier, and I'm going to tell more about it here in a second. The idea is to stage information inside a larger system for tools that are not iRODS to do some analysis and then get that stuff back in iRODS. So the Braini project itself is a collaboration here at UNC in Chapel Hill, North Carolina in the US, and basically three groups. It's RINC itself, the Renaissance Computing Institute at UNC. And so Steve Cox is Director of Software Architecture here at RINC. And so I'll show you a picture shortly about all the fabulous things that are part of that project coming out of that effort. And then myself at the consortium doing the iRODS piece and making sure that we can kind of span the systems and make sure that things can talk to each other. And then we've got two partners over in the School of Medicine. Michelle Itano is Director of the Neuroscience Microscopy Core, the NMC. You'll see that acronym a little bit later. In the School of Medicine. And then also Stein Lab, Jason Stein and Oleg Krupa. So Jason's the director of the Stein Lab, and that's in Department of Genetics and the Microscopy Core, also in School of Medicine. And one of the interesting things about spanning from RINC to the School of Medicine is all of the kind of firewalls and protections and things that the School of Medicine obviously has on their networks, and keeping the storage and things at RINC. So this is it's almost like working with another school or another university, because it's not our network and it's not their network. So the Stein Lab studies variations in genome affect structure and development of the brain. And so they are doing that with a lot of imagery. They've got some optical microscopes, and they take really big pictures, and they are using mouse brains in large part. So there's not a lot of HIPAA or PHI involved in this particular data set, but the data management problems, opportunities are the same. So this is a picture of the architecture of the Braini project. And so here on the left is what's happening here at RINC. So this is a VMware cluster. This is coming out of Kubernetes, and you'll see, here's metalinks, here's the iCommands. There's one VM, long-running VM, that's got some storage attached to it that's holding the brain scans. And we've got NFS rods deployed, and we've got some other applications and things over here. This is all in a project that comes out of Helix and the software architecture group here at RINC. And so the idea is that Braini images can be viewed and manipulated, and science is done through this kind of cloud top architecture, and get to those through the two different browsers and things. But the storage underneath is kind of managed and handled by iRODS. And then spanning over to the right side of this picture is the neuroscience lab. So this is over in the School of Medicine. And so right now these are two long-running VMs, and they both have storage attached to them, but there's much more storage at RINC. So this is going to be considered the primary storage, long-term storage later in the slides. And so Metalinks has access out, iCommands have access out. But the acquisition and the ingestion is happening only over in the neuroscience lab. We don't have the microscopes over here. So there's only two sides to this coin for the most part. So just keep that in mind as we talk through the examples of what we were thinking through. So the use cases that we developed were with the people in the room. And the idea was to take a kind of blue sky approach to this. There are not so many people in the room that we can't decide what we like and do the nice things, so to speak. And so the people involved really are the scientists doing the work, the technicians in the lab who are not necessarily the scientists doing the capturing. And of course, various political aspects of being a director and having money and moving things around and having people for that. And so we had, the two different cores on that. Obviously, there's moving parts inside of RINC, both in terms of dollars and storage, but also access to people and time and long-term commitments and things like that. And then, of course, the iRODS part, who's doing the work, who's writing the code, and how does this work long-term, who's maintaining it over time. So over the course of 2 to 3 months, we had our, bi-weekly meetings and kind of worked through these use cases and talked it out. And just to give you a sense of scope. And so we're going to go through the process, and I actually pulled the most of the text for the rest of these slides out of our design documents that I went back to and found them, and they're remarkably readable, which was great. So going round and round, we basically defined 4 main use cases and agreed to them and started moving forward from there. And so the first one is really about the front door. We've got to get data into iRODS, and how is that going to happen? And remember, the data was going to be created, formed in the lab on the microscope machine, so to speak, and that data needs to get into iRODS. And so that could either be done, through a web client or an iPut, or maybe there was an automatic ingest or something. We have a landing zone. So we talked through that, and we decided in the end that, a well-known location on a space in the lab where data could be dropped, or an iPut could happen from that place, would be good enough for now. And that way it becomes, quote, under management for iRODS. And then that lab member, the people doing the work, they expect the data to appear in the namespace, maybe with some particular permissions or some particular metadata. Maybe it was defined by a file coming out of the microscope or some kind of template that needs to be filled out or something. So we could work through that later. But there was some standardization agreed to at that point. And then at that point, the lab expects the data to be handled. So it's in local disk, but it should be moved off somewhere else so that disk doesn't fill up. They don't have a tremendous amount of storage available to the machines in the lab. And so once it's in iRODS, it needs to kind of get somewhere else magically, right? And so this was our speculation at the time of kind of where that was going to be and how that was going to work. And so the proposed solution for this is, well, obviously we need some storage tiering. And if we want to automate the ingest part, then we could have something watching a landing zone if that's what we want. But that's kind of an optional second part. So storage tiering was the answer to use case 1. Use case 2 is extremely similar. These words are almost exactly the same. Really, the only difference is about whether things were on that local machine after the fact. And so this last sentence, where the import files are moved to some kind of analysis folder, the idea being that you ingest it, and then it's still available for analysis by some other tool that's sitting in that lab, some other system that doesn't know about iRODS and isn't going to learn about iRODS, right? They just want to be able to point it at a certain file and draw a picture. And so this was very similar in terms of the use case. And so the solution was also the same. Once it's under management by iRODS, storage tiering can take over. But then there was this twist of maybe we can use some metadata to annotate something in iRODS, and then that would kick off some policy and maybe put it back somewhere, maybe in the same place. But then you have the concept of it being read-only. You really don't want something that's under management by iRODS to be touched by one of these other applications. So there's a tricky bit around where does it go and who can touch it once it's under management. And so we decided that any products from local analysis, say, new images or thumbnails, or, if things were tiled or whatever, those would get routed back through whatever front door that we built, basically use case 1, to get that new imagery or whatever back into iRODS. Another candidate here was NFS rods, but we had seen concerns about network latency, and knowing that these systems are in different networks, That was probably not going to be our first choice, but it's a candidate, it's a possibility. The third use case was similar to that analysis, but without the kind of import part. Slightly different wording. This was more about utilization of that machine locally, because they want to use a custom Python script or maybe some MATLAB code or something like that. And, you know, but they don't want to use up all the CPUs, you know, maybe some kind of queuing system, you know, leaving things in there for a little bit of, you know, this seemed more about job scheduling and you know, time and power management inside the lab machine. And so this turned out to, we basically agreed that this wasn't something that iRODS should try and solve. Basically, if something's under management by iRODS and it can stage something in a read-only fashion, we think it would solve this use case as well. But basically, you've got this concept of it needs to be around for a while, but then it needs to be removed from the local drive eventually in some timely manner, so that that limited amount of disk space does not fill up in the lab itself. And then the last use case, this is about external users. This is about people who are not in iRODS. How do they see any of this work? This is a lab. The coin of the realm is publications, and at this point, you know, it's not real unless we've got your data and your methods and all of that stuff, maybe even the code that did it. So we need to get the published data in an iRODS way available for download and even to the public. So they were interested in finding out whether a request was legitimate. They wanted a little bit of metrics around how many times the file was downloaded and who downloaded, or maybe requiring an email address. And so immediately, you know, questions about identity and verification and authentication and, you know, all of that stuff come up. And I think that was eye-opening for the lab. They, you know, they hadn't considered the technical aspects of what that entails. But then, you know, as soon as you start asking questions, like, well, we don't really need to know who it was, as long as, well, maybe we do, except for this one case where we want an email address. So we talked through that for a while. We also wanted to make sure that, you know, downloading these things, these are huge data sets, and that one little machine in that system might not be the best place to kind of, you know, hold the hill and download all the data out of their lab. So the solution was going to be a combination of storage tiering and making sure something's available. Maybe if you label something in a certain way with metadata, it could be staged or published in some way. And then we basically decided to work on this later. So this was a nice to have, and went to kind of the bottom of the pile for these list of 4. So after talking all this out, the design goals basically became 3. We needed some kind of storage tiering to get over to primary storage at RINC after acquisition or creation in the lab. We decided around some manual targeting for local analysis. So something needed to be written to do the staging, do the replication, do the trimming for all those cases when it needs to be here for, you know, the Python scripts, the MATLAB, whatever. And then the last part was this thing that we said, well, maybe we'll do later. Same approach, you know, add some metadata to something, and now it is considered to be published or published, and maybe create some kind of little state machine around those states, and make sure that files can be available for others for download. And so once we agreed on what needed to be done, what does that actually look like on the ground? We decided there were 3 storage resources. There were going to be 2 on the workstation. Remember, that's the one that has the limited supply of available space. And then the primary, which, you know, for all intents and purposes of the microscopy lab, is effectively infinite, right? It's more. So that's where the primary storage is going to be at RINC. If we were going to do automated ingest, then we would do that and point the registration of things in place into that NMC ingest resource. And that would be a bit of magic. They would drop something in and it would just take care of it. It would show up in the right place. And then coupling that with anything that's in ingest would storage tiering its way out over to the primary at RINC, and that could be configured to be handled at some amount of time. I think we ended up going with 12 hours. So things sit in NMC ingest for about 12 hours, and then magically, we don't use that word, predictably, they make their way, they replicate and then trim, they make their way over to the primary storage at RINC. And then in terms of the local analysis use case, where we want to be able to tag something and have it be available in the workstation. So the idea is that we're going to trigger on the PEPs around metadata add and remove. So if someone adds the magic pixie dust to a particular file or something, a collection, it would replicate that in the background or synchronous, I think it was asynchronously, within a couple minutes. It's going to replicate the thing that was tagged over to the NMC analysis resource, which is on the same workstation. It could be a different place, but in this case, there's only one machine in the lab running iRODS. And then it would also run a little script to set physical permissions. This is still something that's in the vault on that analysis resource on the workstation, and set it to read only for anybody else on that machine. Now, they couldn't touch it, they couldn't delete it, they couldn't update it, but other tools like the MATLAB script or the Python script or whatever could read those files and be able to do its own analysis. And if they produce new outputs, those have to go back in the front door. Those get put back in the ingest place. And then obviously a corollary bit of scripting is around removing the metadata. So if you remove the magic pixie dust from the file, then all you have to do is trim the replica that's sitting on analysis. At that point, it's still over in primary. It wasn't removed from primary. And everything is still the way it should be. And then for the publishing use case, which we decided to do a little bit later, was again looking for a slightly different magic string, an AVU, and it would do replication or check something or create a DOI or send it to somebody. We didn't get to that part for this first pass. And so kind of stepping back and looking at what we produced, the effects of those really are there's always a replica in primary storage. So that's a big deal. We set the minimum restage tier to RINC primary. So it never restaged all the way back out. That's a storage tiering feature. And then we set that not necessarily to real time. We set it to 12 hours, and that was a nice balance. We haven't had to change that, but it's literally one or two character change in the configuration. This allows for that manual tagging. So if someone deems a certain thing ready to be looked at by some external script, they can just put some metadata on the thing and it shows up in the analysis area within a few minutes. It also allows for the future manual tagging for publication. And then something not to be forgotten, all of those cloud apps that were running in the RINC infrastructure, they always pull from the primary at RINC, and they don't trigger replication, nothing moves around, the tiering doesn't affect those. So they're always available and they're relatively local to those VMs and Kubernetes style containerized applications. And so the actual implemented policy to do all that, it was a set of policies that had to kind of play together, and we handled data analysis, replication, and retention from the microscopy core. And there were two parts. There was an automatic part and a manual part. And this text is pulled directly out of the repo that I link later. The automatic part is strictly all about storage tiering. So that was an out-of-the-box experience from my perspective as the policy developer. All I had to do was install storage tiering and configure it a couple different ways, and the rest of it just worked. So that handles the newly ingested data. It moves it over to RINC after a certain amount of time. RINC is providing the storage and the visualization tooling, and all that's kind of handled, and it's only talking to its local storage. The second half of this is where I spent the most of the time writing the new code. So this was about the local analysis. They can tag the data of interest. The policy then picks up and replicates that information, the data over. It sets the permissions, and most importantly, it prevents removal of that data. So nobody can manually run itrim and delete the thing in that system. It is in flight. It's considered in analysis, and therefore you can't touch it. So once somebody untags it, then it's trimmed by the system, and everything else goes along the way. So here's the storage tiering one pager to kind of give you an overview of how that works. This is the one pager that we've had for a few years now. And this depicts a 3-tier system. Turns out what we built was just a 2-tier system. And it's not because we wanted something that was fast, intermediate, and slow like this depicts here, but rather we wanted something that was, quote, local and then long-term, right? And again, it doesn't matter the reasons that you pick the tiers, but we had 1-tier group with 2 resources in it, one sitting at tier 0, one sitting at tier 1. And to go back to this picture is flipped left to right from the last picture, of course, naturally, because the microscope is on the right here. So the brain scans that come in from are considered tier 0 from the microscope over in the lab, and then tier 1 in this case would be over here in RINC. So that was the automatic piece. The manual piece, these are the cases that it turns out that matter. So there's a check mark here. This is a run of the BATS test. This is a bash testing framework. And these are the events that we care about. Someone can sprinkle the pixie dust on a collection. And what that means is that then everything underneath it gets replicated over, and that works fine. We have a test around doing the same thing for a data object. That's a simpler test because it's only one data object. Then we have a test around untagging, so removing the magic tag. That would then do the trim from the analysis area. We have cases here around overwrites, which are interesting. If you overwrite a tagged data object, meaning it's already tagged and it's over in analysis, then that should update the one in primary and then automatically replicate and update the one in the local storage. And so those are allowed, and that works, and it keeps everything up to date. And so you're always looking at good replicas no matter when you look at it. And then the rest of these, the last, 8, 9 cases here are all disallowed by the policy. So you are not allowed to trim a data object that is under analysis. You are not allowed to trim a data object that's under a tagged collection. You cannot remove, so IRM does not work for the same cases. And then there's also removing a collection which contains a data object that is tagged is also disallowed. So these are the cases where otherwise your system would not be able to enforce the integrity of what's going on. The last one is untagging an in-queued data object. If something is in fact in-queued for replication but has not yet been replicated or moved, then that's disallowed. You have to wait for the delay rule to occur before you can get rid of the tag. And then the same thing with a descendant data object under something that's in a collection. So these were the cases we worked out, and I'm pretty sure we've captured all of them. It's an interesting exercise, but we did not have to change into the original architecture. It was just a matter of writing the Python in such a way to tell the rule engine policy in the pre, just to say, no, you can't do that. And then give an error back to the human. And so right now there is actually nothing in flight. I ran these last night. Nothing is sitting in ingest, nothing is sitting in analysis. I think it's mostly because Oleg graduated and now they've got to find somebody else to do the work. But there's 921,000 data objects sitting in RINC rest and taking up about 12 terabytes, almost 13 terabytes. And so it is real, it is working, and I think we're looking for kind of the next set of use cases. We are looking to add the automated ingest, and that's probably not going to take up too much time to do. That's just a few more moving parts to make sure that we agree on what things should be named and where they should be. We talked about the publication possibility. And again, that's just going to be some more BATS tests to make sure things are behaving. And obviously adding, additional microscopes, additional machines. That might mean more landing zones. It might mean more complex topology inside the tiering groups. but nothing that the framework shouldn't be able to handle. And then obviously, you know, with this wild success, we've received some interest from other labs in terms of doing the same for them, or getting access to the images, or maybe the tooling inside and around the images. And this is, so from our perspective, from the iRODS namespace perspective, this is a project that's just an example of how to do policy. So this is a Python project, and it's sitting in there, and it's really just a couple Python files. This is the extent of the configuration for the actual code, and then there's a couple things that need to be done in terms of adding a specific query, or adding a query to the storage tiering engine. This little script is the one that sets permissions for the read-only. And then this is the AVU that we agreed to. So an A of NMC, a V of analysis, and an empty U is this is the magic pixie dust that causes the analysis tagging stuff to kick in. And this is the metadata that's associated with something that is has been tagged but has not yet been moved. And so that's how it's the equivalent of the intermediate replica for fans of what Alan's been working on the last year. And I think that is it. So I'm going to look to my left. If I can't see the chat, I'm going to look at Slack. Also, I suppose I could, if somebody wants to raise their hand, I could click on people too. Let's see. So Alan's asking, have you considered implementing the compute to data pattern for the NMC analysis use case? And that's, the pattern there is to be able to send the science to where the data is. And for the most part, because the data is always in the primary storage at RINC, all of the fancy GPU attached analysis tools are already considered local to where the data is. The types of things that were being run on the local systems in the lab were not necessarily where the compute was. It's just that that's where they had the MATLAB, that's where they had their microscopy situation. So this is not necessarily that directly, but if, say, we had another partner or another data center, or maybe a different computer where all the GPUs were inside RINC, then that could be possible. We could route things accordingly there. But that's not necessarily part of the iRODS policy as much as it would be the cloud top infrastructure that's been stood up right now. And then, yeah, so Jason's answered that a little bit with the Helix infrastructure. The NFS RODS part I did not talk about here, but all of the tooling inside the Helix infrastructure, the Kubernetes stuff, is getting access to iRODS through NFS RODS as well. So they're still going through the policy layer. Everything is still firing accordingly. And then Chris is talking about Python, so you tripped me up there. And then Ronnie from KU Leuven says, how will you manage deployment and updates of local storage resource servers in the labs? So that is a question that we're getting to now. Right now, I think the plan is to add another disk or 3 or something to that machine, and that will require us to change how the storage tiering works if we want to, for the automatic piece. For the manual piece, it would we would need to make sure that the local analysis went somewhere. And if we needed to set up a second set of magic pixie dust, so to speak, we wanted to go to a different place, then we might have to target that specifically. But it shouldn't be too complicated. It's just a question of you know, naming things well and adding capacity. Right now, if they add another machine that had certain tooling on it, we would probably just stand up a parallel set of manual tagging policy. And Ashok says, will the derived data from Helix analysis land back in the iRODS managed areas? So that's a good question. That's on the other side of the equation. So yes, anything that comes out of Helix could be put directly back in through NFS RODS, because NFS RODS is you know, not read-only. So it could go back through that tooling. It could go back through a different interface, but probably the idea is that we don't want to teach all of the analysis applications in the world how to speak iRODS. That's not feasible. That's part of the reason NFS rods exist. So yes, if the Helix tooling produces new things, then they can go through the same file system with the same permissions as they have access to them. And if they want to have a different set of permissions, then that's just another conversation. All right, I think we did it. Any other questions? All right. Thank you, and we'll get started with our panel at the end of the day.